Hello, welcome to the torques unit. So this video is just a brief introduction to torque, which sometimes is called moment in engineering terms. So if you're in construction or engineering technology, you'll probably be having some courses where you're talking about moments, but they're just torques. That's what physicists call it. So the torque unit is really good for your intuition. Your intuition is going to be very helpful here because it's going to be right. And so to start with, I just want you to think about opening a door. So when you push to open a door, where do you push to have it open the easiest? Do you push on the, if the door is like this, do you push on the hinge side over here? Do you push in the middle? Do you push on the side away from the hinge? Where do you push in order to have it open the easiest? You know the answer. It's away from the hinge, the side that opens. Because you've probably had the experience of having one of those push bar doors, and you push on one side and it barely moves, and you're like, probably the other side, push, it moves. Yeah, so you already know that where you push on a door affects how easy it is. And that is really the idea of torque. That's one of the basic ideas of torque, is where you push on something affects how much it rotates. We used to be talking about forces causing motion linearly. So we talked about linear motion. Now we're going to be talking about rotational motion. And torques cause rotation just like forces cause linear movement. And let's see, what else? I want you to get a ruler. So hit pause, go get a ruler. And what I want you to do with that ruler is put it on the table. So set it on the table in front of you and gently hold down in the middle so that it can move about the middle, but it won't slide in any direction. So it can rotate, but not move sliding. And I want you to, let's see if I can do this here. I want you to push on the ruler in different places and see where you can push to make it rotate. All right, you probably already found 3. So how many different places can you make it rotate by a push? So do that and you'll say, okay, I can make it rotate there, all sorts of rotations. Now, I want you to find 2 places, or more, at least 2, where it won't rotate when you push on it. So, where could you push on the ruler so that it won't rotate? Play around with it and hit pause. Once you have at least 2 places, come back to the video. So hopefully what you found is that 2 places you could push would be right here, right at the pivot point, and right here, right at the end, which again is pointing directly at the pivot point. So if that's our pivot point, kind of our hinge, if I push right, aiming at the pivot point here, or push right at the pivot point here, no rotation. Push here, or here, or here, or here, anywhere else, we do get rotation. So that's a second piece to torque. Where you push and how it connects to the pivot point. The pivot point is going to be pivotal for this unit. So sorry, I couldn't resist. So where you push and where it is relative to the pivot point makes a huge difference. When you're trying to push open a door, what's the pivot point? Well, it's the hinge. So farther away from the pivot point, it's easier rotation. All right, close to the pivot point, it's really hard. It takes a lot of force in order to get that door to open. If you're aiming a force directly at the pivot point, you're not going to get any rotation. That would be like pushing on a door. I have something that I could pretend to be a door. So here's a door swinging like this. If I were to push on the skinny edge of a door, it wouldn't cause any rotation because I'm pointing at the pivot point. Likewise, if I could get above or below the door and push right at the hinges, right where the hinges are, no rotation. So you have good intuition about torques. Follow that intuition. Another thing I want you to think about, again, intuition is good, is the idea of how much force it takes to do something based on where that force is applied. So I've got a broom thingy here, and if I hold it in the middle, oh boy, if I hold it in the middle, it's really easy for me to lift it up. However, if I try to hold it at the end with the heavy weight over there, trying to hold it horizontal takes a lot more force, whereas if I hold it, let's see if I can do it this way. If I hold it close to the weight, then it's not that hard. And if I can find just the right point, then it's barely any work at all, and that's the pivot point. Because if I'm off the pivot point, then the force I'm dealing with is different. Well, there is a torque based on that I'm exerting a force away from the pivot point. So again, comparing back to what we've been doing, previously we've been talking about forces causing linear motion. So if I drop this, the force of gravity, which acts at its center of mass, is going to cause this thing to move in a linear fashion. It's going to accelerate linearly straight down. Now I'm going to be thinking about how forces cause rotation. So if I'm holding this at the end again, I'm going to cheat like this. There is a force of gravity at the pivot point that's causing a rotation around the pivot, which is my hand. So my hand is the pivot, and gravity's saying, oh, I'm trying to push that thing and make it rotate. So we're thinking about rotations now instead of linear motion. And just like with forces causing acceleration, linear acceleration, torques cause rotational acceleration. Now, this unit, you're going to like this. All we're going to be talking about with this unit is static equilibrium. Things aren't moving. And think about back with forces. If things aren't moving, what's the acceleration? 0. If there's no acceleration, what do we know about the forces? Balanced. Balanced forces. The sum of the forces equals 0. So when things are in static equilibrium and not rotating or moving, that means the forces have to be balanced, but it also turns out that the torques have to be balanced. So if something is not rotating, that means all the torques on it have to equal out. All the things that make it want to rotate one way have to equal all the things that make it want to rotate the other way. So what we're doing with torques is kind of an extension of what we did with forces, but we're moving into a rotational kind of frame of mind than the linear frame of mind. So what is a torque? Well, okay, we have a definition for torque, and again, it's moment is the other name for it. It's given the symbol Greek tau, T-A-U, which is this kind of curly T thing, tau. And we have different equations that we can define torque with. If you are thinking in terms of calculus, it's a cross product of R and F. Okay, what would these things be? R and F, what could those mean? Well, F, you probably have a sense of what we were talking about, force. You push on something, it might cause a rotation. What would R be? R is typically a radius, but in this case, it's a radius from the pivot point. It's actually a distance. We're going to talk about it as a distance from the pivot point. So here's one definition of torque with a cross product. That's the calculus way. The next one is the one that I typically use the most, F perpendicular times the radius. The perpendicular force times the radius. There's an alternate one, which is the perpendicular radius times the force. And then the one that you'll see when you have when you're watching Dr. Hop's videos would be FR sine theta, and theta is from R to F, because how you figure out an angle is really important. So here are a couple definitions of torque. And the one that I use in my examples is that one. I think about a perpendicular force. Now, what the heck does that mean? Let's go back to the ruler. So get your ruler again. If you have the ruler and you push on it, okay, yep, we get a torque, we get a rotation. What if you push on it at an angle? So if I push on it at an angle, I still get a rotation. Is it as big of a torque? Is it as big of a rotation as if I'm pushing straight? No. Give it a try. Try pushing straight and then at an angle, at a really shallow angle, at a really steep angle. Which is the biggest torque? What you're going to find out is it's when the force is perpendicular to the radius. When we have our ruler here, I'm actually going to draw it. When we have the ruler like this, and we have our pivot point right in the middle, that's where we're keeping it still so that it could rotate about that point. So that's our pivot point, PP. Then when we exert a force, let's say we exert a force like this, the distance from the pivot point is from the pivot point to where the force acts. That's our, what we're calling R, kind of the radius. It's also called the lever arm. And so we have this, and when they're perpendicular, you get the biggest torque. Now let's suppose we do a really shallow angle. And it's the same force at the same point, then it's not as big of a torque. So R is the same. These two forces are acting on the same point at the ruler, but this isn't as big of, this doesn't cause as big a torque as this one. And the angle that we're thinking about, the angle between R and F, okay, I've got this part and I've got this part. If this is an angle, I don't know if I did that right. Yeah, I did that right. Which component causes a torque? Well, there's a component of this force, the horizontal component, is effectively pushing on the ruler in this direction. We already know that pushing on the ruler in this direction doesn't cause a rotation, doesn't cause a torque. This direction definitely does. And so it's that sine component of the force that causes torques. The cosine component doesn't cause a torque because it's in the same direction as that radius, that lever arm, and so only this part causes torque. This part doesn't. So that's why we're going to be talking, you're going to see a lot of sines. And the cross product tells you that it's this, I gotta be careful, this component as well. All right, so let's do an example of calculating a torque with an angle. Here is the question. Revolutionaries attempt to pull down a statue of the great leader by pulling on a rope tied to the top of the statue's head. The statue is 17 meters tall, and they pull with a force of 4,200 newtons at an angle of 65 degrees to the horizontal. What is the torque they exert on the statue? If they're standing to the right of the statue, is the torque positive or negative? All right, so problem solving process. You already know the first step. Draw a picture, right? Draw a picture. So we've got a statue and people have tied a rope to its head and the people are pulling on it. And they're to the right of the statue. The statue was 17 meters tall and they're pulling with a force, so the pulling force is 4,200 newtons. And the angle is 65 degrees to the horizontal. Okay, so this angle is 65 degrees. We want to know what is the torque that they're exerting on the statue, and is it positive or negative? All right, so using the definition of the torque that I typically use, I'm going to use torque equals the perpendicular force times the lever arm, the distance. All right, one of the things you're going to have to do first is figure out where's the pivot point in any of these problems. So if you're pulling on the top of the statue, where is it going to pivot about? Don't worry about, well, if it starts to pivot here, then it might slide and, just go with your gut instinct on this. and it'll usually be right. So I would say that the pivot point is at the base. If you're pulling on something at the top, I'm going to say it's going to try to pivot like that. So the pivot point for this problem is at the base. Now we need to figure out what is the perpendicular force and what is the lever arm. All right, so the lever arm, the distance, R, is from the pivot point to where the force acts. So in this case, R is from the base to the top. We know that's 17 meters. What is the perpendicular force? All right, so this is where we get into components. The force is 4,200 newtons, and okay, if that's, oh man, then this, I didn't do this very well, 65 degrees, like that. Okay, we have a triangle, and we have the two components. Do we want the sine component or the cosine component for the perpendicular piece? So here's our F, here's our theta, here would be the cosine side, here would be the sine side. Which one in this case is going to be perpendicular to the lever arm, to the distance? Well, my lever arm was like this, which means the perpendicular component of the force would be this part, which is F cosine theta. All right, so we've got the torque equals the perpendicular force, which is F cosine theta, times R. 4,200 newtons times the cosine of 65, it was 65, right? Yep, times 17 meters. And what do you get? Well, how about if I actually wrote the answer down? Oh, it's a big number. It's a big number. This is a huge torque. Oh my gosh. Okay, 30,175. What would the units of torque be? Well, okay, cosine doesn't have a unit. Force, that has units of newtons. Distance, meters. So the unit for torque that we're going to be dealing with is a Newton meter. So the torque here is 30,000 Newton meters. You can have really small torques. You could have torques this, it's like 10 Newton meters for a really, really, really little thing, a little force. Or you can have things this big. The range we're going to see is probably, the typical range we'll see is hundreds to maybe 10,000. That's, I would say, the typical range. Now, we haven't answered the full question. We need to know direction. Is it positive or negative? The direction of torques is dependent on the way that it wants to make something rotate. And the convention is kind of, unfortunately, backwards from what you might want it to be, because it is based on the cross product that I mentioned with the calculus definition, the cross product of the two vectors. If we have a clockwise rotation, if a force wants to make something turn clockwise, that's actually a negative torque. Counterclockwise rotation would be a positive torque. Now this isn't what the actual rotation is, because the objects we're going to be dealing with aren't rotating, they're going to be holding still. This is what would the rotation be for this force. So I have an object like this, it's pivoting down here, and I'm pulling down on it, like that. So I'm pulling down on it. Is this a clockwise or counterclockwise rotation? Well, this is a clockwise rotation, and clockwise means negative. So the torque, in this case, is a negative. And let's see, yeah, okay. So the torque in this case, we have a negative 30,000 Newton meters. That is the answer to the question. We've got the value of it and the sign of it. All right, so I had mentioned that we're going to be doing just static problems, static equilibrium, where there's no linear motion and there's no rotational motion. When we think back to no linear motion, okay, if it's not moving, What does that mean about the acceleration? You already answered that. Acceleration is 0. And if the acceleration is 0, that means the sum of the forces is 0. And this is true in both directions. So we actually have two equations. This I put that in the wrong place. The sum of the forces in the x direction has to be 0, and the sum of the forces in the y direction has to be 0 if there's no motion. Now we're going to say that the rotation equals 0. There's no acceleration in the rotational direction. What does that mean? Well, it's a direct translation. If there's no rotational acceleration and rotations are caused by torques, that means the sum of the torques has to be equal to 0 as well. So for torques problems, you've got three equations that you have available. You can add up all the forces in the x direction, set them to 0. Add up all the forces in the y direction, equal 0. Add up all the torques, set them equal to 0. Three equations. Easier problems, you're going to use just one or two of the equations. For the harder A-level torque problems, you will need to use all three. And so get in the habit of thinking, I have three equations available. What are they? Which ones are going to get me what I need? In general, there is the problem-solving process for torques is going to be very similar to the problem-solving for forces. Instead of what we call the usual free body diagram or force diagram, we're going to be doing an extended force diagram. And the next video is going to show you how to do those extended force diagrams for torques. But other than that, this is the key. This is what we're dealing with. So here's the definition of torque that we're typically going to be using. Here are the rules for the sign convention. Clockwise is negative, counterclockwise positive. And here are the three rules for static equilibrium. Let me just remind you, this is only true for static equilibrium. When nothing's moving, nothing's rotating. And that is the basics of torques. Good job for watching.